This unit will cover beams. The file name for this unit is phys0008slides14.pdf. It has nothing to do with Mazur chapter 14, which we will not cover in this course. This set of slides in fact covers Onouye Kane chapters 6, 7, and 8. Chapter 6 is about cross-sectional properties, which should help you to understand why, if you take a so-called 2x10, for example, dimensional lumber, it is not very stiff if you use it as a plank, but it is quite stiff if you use it as a joist. So its stiffness when it is on end is much bigger than its stiffness when it is on the flat. And you can also understand why an I-beam has the eye-like shape that it has, and again, why this shape is much stiffer than this shape for supporting a vertical load. Then chapters 7 and 8 will talk about how we analyze beams. You might wonder why we study beams, and in fact maybe even why we study trusses in a physics course. One reason I chose for us to study trusses is because they are a direct application of what we've learned about the rules of statics and static equilibrium. And trusses appear pretty commonly in ordinary life. If you look at a railroad bridge, if you look at the roof trusses in a wood frame house. And even though the analysis of a complete truss using the method of joints is quite intricate, it's really the intricate application of a few straightforward rules. So it is amenable to straightforward pencil and paper analysis, even if that analysis is pretty tedious. And then of course we moved on to using the method of sections, which allows us much less tediously to find just a few bar forces in a truss. Similarly, the analysis of simple beams appears in many introductory physics courses. So many Physics 101 type courses have a unit that covers beams and columns. Again, in terms of connecting physics to everyday life, if you walk around and look at the built environment, if you go into the basement of a wood frame house, you see a network of floor joists. And sometimes it's interesting to stand there in the basement of a house and to ask why the floor joists that you can see have the size that they have, and how that size depends on the presence or absence of mid-span supports like a column or a mid-span beam. Like trusses, beams can be analyzed using pretty direct applications of the methods of statics that we've studied in this course, although it's a kind of a step further from what we've seen so far. So there's a bit more new terminology and nomenclature in the study of beams, even simple beams. We won't do anything very complicated than there is just to analyze a truss. So you have to learn a bit of new vocabulary, but I still think it's a worthwhile way to get some new insights. Maybe yet another reason we could talk about trusses and beams is that they appear near the top of Professor Farley's list from his structures course of basic elements of architectural structure. If we look at his slide, the first element he lists is a beam, which he describes as something that takes a one-dimensional path to span one dimension, and then its close cousin, the column, is something that may be worth adding to this course. It's an extra credit option right now. Just a step down in Professor Farley's list are the frame and the truss, which are built up of members that are basically one-dimensional in nature, but which span a two-dimensional region. So when you look at a drawing of a truss, it fills 2 dimensions on a sheet of paper, but you're analyzing one-dimensional bars that compose the truss. And it seems that he puts the classic arch in the same category. Continuing down Professor Farley's list of elements of structure, you see things that we don't talk about at all in this course, and you'll just have to wait for Professor Farley's structures course to see for real. So in this course, we try to study examples that can give us some insights about architecture, but that don't take us very far away from the realm of physics, because this is, after all, a physics course, and I am, after all, a physicist. And I really depend completely on Professor Farley and on textbooks like the Onouye book for insights that go beyond my own expertise. So last video, we saw two kinds of external forces acting on trusses. We have loads, like this 1 kilonewton force, and the whole purpose of the truss is to bear the load forces acting on it. And then we have the support forces, sometimes called reaction forces, which are basically the forces exerted by the ground on the truss to hold it in place. I drew a little triangle on the left to indicate a hinge or pin support, and I drew a little roller or a circle on the right to indicate a roller support. So this can have both horizontal and vertical components, and this can have only a vertical component, or only a component perpendicular to the surface below. So if we call these left and right points A and B, then we would often start the process of solving a truss by solving for these support forces AX, AY, and BY. Sometimes we didn't have to do that at the outset. Sometimes the truss geometry was such that it was easy enough to go on to directly applying the method of joints, joint by joint, without first solving for the reaction forces. But in many trusses, we had to start first by solving for the reaction support forces. Then we went on to solve for the internal bar forces in the truss. So looking at the forces acting on the truss, we had the load forces, which the truss bears, its purpose for being there. We had the support forces, also known as reaction forces, which hold the truss in place, typically exerted by the ground below. And then we had the internal bar forces. So now we're moving on to talking about beams. So if you've looked at the joists holding up the floor of your house, if you look around the basement of your house, then you're kind of familiar with the idea of a beam. So beams carry loads. Like here's an example of a vertical force in magenta acting on this beam, a vertical force that I've given the value 1 kilonewton and labeled with the name P. And then there are support forces, analogous to these support forces exerted on the truss. So here's a pin support on one side and a roller support on the other, which is typical. This configuration is called simply supported. So a roller support on one end and a pin support on the other end. And typically one of the first things we do with a beam is to solve for these support forces. Any load applied to a beam in our simplified treatment of beams in this course will be vertical. So this horizontal support force will always be 0 in the beams that we discuss. But in general, for a simply supported object, there could be a horizontal force here, a vertical force here, and a vertical force here. So given the value of this load or other load forces and the relevant dimensions, so we know where along the beam each load acts, we could solve for these support forces, which in this case are called AX, AY, and BY, using the familiar rules of statics. So far, that's just a familiar statics problem. You have some set of forces acting on an object. You know the line of action of each force. You can solve for up to 3 unknown forces. So this force that we called P is a concentrated load, a force applied at one point along the beam. And we could have more than one of them. So we could change this one's name to P1, and maybe we could have another one, P2. We could have several of them. And you would know how to solve for AX, AY, and BY using the familiar rules of statics as long as you know the values of these applied forces and you know where they act along the beam, you know the line of action of each applied force. All of the forces that we've considered in statics problems so far act at a point. In that sense, they're similar to these concentrated loads. A concentrated load like this would be analogous to putting maybe a safe or a very heavy dumbbell at one point along your living room floor. What if instead we wanted to support maybe 100 people spread out uniformly along your living room floor? Maybe we want, instead of saying that there's one particular force here, there's one particular force here, to say that we're designing this beam so that it supports some force per unit length along the beam. So if we have some uniform force per unit length along the length of the beam, maybe it's like a dozen identical people all standing side by side and you smooth over them so it just appears like uniform force per unit length. We call that a distributed load. And a distributed load is usually represented with the lowercase w. So lowercase w is downward force per unit length exerted on the top of the beam. So the symbol P typically denotes a point load, a concentrated load. The symbol lowercase w typically denotes a force per unit length, a distributed load. So we've never seen that before. The first thing we want to know is how do we solve for these forces AY and BY? AX will still be 0 if all the load forces are vertical. The trick that we use to solve for the support forces AY and BY is we replace the distributed load with a so-called equivalent concentrated load. It's equivalent in the sense that if we do things right, we'll get the correct support forces, AY and BY. It turns out that the shape of the beam, when we put the load on it, will be different depending on whether you put all of the load in the one place or if you spread it out. But we won't consider that until later. For now, we're interested in what do we have to do to get the support forces. To find the support forces, AY and BY, we temporarily replace each distributed load by an equivalent concentrated load. By equivalent, we mean it will get us the correct AY and BY. So we make that replacement. We then use that equivalent concentrated load to solve for AY and BY, the support forces. Then we undo that and go back to the way the beam originally was drawn because we typically want to move on and study things like internal forces in the beam or the deflected shape of the beam. How do we know what this equivalent concentrated load is for this distributed load? Its location is the centroid. Centroid is another word for center of gravity. Its location is the centroid of the distributed load, and its magnitude is the total force. So if this distributed load were 100 newtons per meter along the length of the beam, and if the length of the beam were 10 meters, then the total force would be 10 times 100 is 1,000 newtons. Then the equivalent concentrated load would be 1,000 newtons located in the middle of the beam at x equals L over 2, or x equals 5 meters. So we would temporarily replace this distributed load with a single concentrated load at the centroid. Centroid of the distributed load is right in the middle of the beam, since this is a uniform distributed load going from end to end of the beam. And the magnitude of that concentrated load would be W times L, just a total force per unit length times length. So in general, W times L would be that force, and then located at x equals L over 2. Now, we didn't have to have that distributed load over the entire beam. Maybe it turns out that this distributed load only covers half of the beam, maybe just the right-hand half. In that case, the centroid would be here 3/4 of the way along the beam, and then the value of this force would be W times L over 2, since now it's still force per unit length W, but now the total length of this distributed load is just half the length of the beam, L over 2, instead of the full L. So if you like calculus, we can do this more formally and say that the magnitude of this blue arrow is the total force, which is just the integral of W over whatever the relevant length is. And then the location is the centroid. Centroid is the same as the average. So to do the average in calculus, you take the density, force per unit length, multiply it by x, and then you integrate that, and that's in the numerator, and then the denominator is just the total force. So this is basically the average position within this distribution. And you know that this thing is uniform. It's like a rectangle. So the average of a rectangle is just the middle of the rectangle. So this is sort of like saying fact, it's really exactly like saying we have this orange rectangle here, and the size of this blue arrow is just the area of this rectangle. So it's how wide is it is like the length along the beam, and how tall is it is the force per unit length. So that area is the magnitude of that blue arrow, and the location of that blue arrow is the centroid of this rectangle. You know, for a rectangle, that's just the middle of the rectangle. The horizontal centroid is just the horizontal middle. Of course, for a rectangle, the vertical centroid is also the vertical middle. But here we only care about the horizontal component. Now, a distributed load doesn't have to be uniform. In some weird cases, you might get a different shape, like a triangle. So here's a triangular load, which means that it's 0 newtons per meter on the left side, and it's some big number of newtons per meter on the right side, and then it ramps up in between. So the number of newtons per meter gets bigger and bigger, starting from 0 up to the end. This is much less common than either something all at one point or something that's uniform. But this is one example of a case we can consider. So in a case like this, it turns out that the location for this arrow would be x is 2/3 L. So it's 1/3 of the way left from the right-hand side. So 2/3 of the way from the left-hand side. So in this case, the centroid location would be x equals 2/3 L. And in this case, the magnitude would be like base times height divided by 2 for a triangle. So that would be, oh, we don't know what this is yet. I'm just going to call the maximum value W max. So then this would be 1/2 times L times W max. So that's basically like 1/2 times the base of the triangle times the height of the triangle. How did I know that this was at 2/3? So we could draw a copy of that triangle over here. So it goes from x equals 0 to x equals L. We're going to call this y equals 0 at the base. And then we'll say it goes from a height of 0 to a height of h on the right side. So then if we pick some point x partway over, then it's going to be at y equals h times x over L. You can see if you plug in x equals L, you get h, and if you plug in x equals 0, you get 0. So we know that the area of this whole thing is the base times the height divided by 2. We could even prove that using calculus if you want. And then maybe a more interesting thing to prove using calculus, you don't have to know how to do this, I just think you might find it fun if you enjoyed calculus, is we can try to figure out where the centroid is along the x-axis. Okay, so using calculus, we showed that the centroid of this triangle is indeed 1/3 of the way to the left of this tall end. So in fact, if you have a right triangle, we could have applied the same argument to the triangle rotated 90 degrees. So if you have a right triangle, then the centroid in 2 dimensions will be 1/3 of the way up and 1/3 of the way to the left of the part that makes a right angle. And then if you have a triangle like this, if you want to find its horizontal centroid, for example, which will be useful in a moment, then we could consider it to be like these 2 right triangles. So then we would have to figure out where it is horizontally, but vertically it's just 1/3 of the way up from the base here. So if the base is horizontal, then the centroid vertically of the triangle is 1/3 of the way up from the base. Or if you have a triangle like this, where there's one side which is vertical, then the horizontal centroid would be 1/3 of the way to the left of this vertical side. So the centroid of a shape in calculus would be defined as like the average over the area of the shape. So you can divide by the total area of the shape, and then in the numerator you have like you're adding up all the little chunks, the area in calculus weighted by x, the position horizontally. And then for the vertical centroid, you like integrate over the whole area of the shape weighting by y, and then you divide by the total area. You don't have to know how to do that. I wrote it that way just in case you like calculus. The only cases we really need to know for a rectangle whose sides are horizontal and vertical, the centroid is right in the middle. So it's x is halfway to the right and y is halfway up. For a right triangle, then if you put the right angle at the bottom left, then you go 1/3 of the way up in height, and you go 1/3 of the way to the right. So it's 1/3 of the base over from the corner, 1/3 of the height up from the corner. If you have a triangle whose base is horizontal, then the vertical centroid is just 1/3 of the height. And we won't worry about the horizontal centroid. And if you have a triangle whose base is vertical, then the horizontal centroid is 1/3 of the way over from that vertical base, and we won't worry about the vertical centroid. So that's the basic definition of a centroid you need to know in order to see what I'm doing in the next few slides. So the centroid is the average position within a shape. The idea of computing centroids of simple and composite shapes is really briefly introduced in chapter 3 of Onouye Kane when they talk about distributed loads. So far we haven't made any really tricky use of centroids. We've just argued, for example, that if you have some force per unit length W on some part of a beam, you can convert it to an equivalent concentrated load, which is the area under this curve, and you put that equivalent concentrated load at the centroid of this rectangle, and that can be used to determine the support forces, for example, at the ends of a beam or some other extended object. So now we can go through a couple of examples using rectangles and triangles and build up a few tools that we can use both to solve for the support forces when a beam carries a distributed load, and also to start to understand how to work out this topic called second moment of area that relates to, let's say, a wooden floor joist, a wooden plank, or the funny shape of an I-beam. First question, looking at the shaded area on this slide, what is the value of x centroid? Well, since there seems to be a symmetry axis in x, there seems to be a symmetry axis at x equals 6, it seems as if it's pretty easy for us to determine x centroid. It looks as if y centroid will be a little bit trickier. So in this case, by symmetry, we can say that x centroid equals 6 because there is exactly the same amount of material to the left of 6 as there is to the right of 6. So I like answer C here, x centroid is 6. What are the areas of the three individual polygons from the biggest to the smallest? Well, this square goes from 1 to 7 in y, and it goes from 3 to 9 in x. So this is 6 units by 6 units. So this is 36 square units. The smaller square goes from 4 to 8 horizontally, and it goes from 7 to 11 vertically. So this is 4 units by 4 units. So that's 16 square units. The triangle goes from 4 to 8 horizontally and from 11 to 14 vertically. So the area of a triangle is 1/2 times the base times the height. So that's 1/2. The base is 4 units. The height is 3 units. So this is 6 square units. So I think I like D. We have 36 square units for the big square, 16 square units for the small square, and 6 square units for the triangle on top. What are the y centroid values of the three individual polygons? Well, the square is highly symmetric, so it must be halfway between the bottom and the top. So halfway between 1 and 7 is 4. 1, 2, 3, 4, 5, 6, 7. You can also say 1 plus 7 divided by 2 is 8 divided by 2 is 4. Here's another square. Halfway between the top and the bottom is 7 plus 11 divided by 2. 18 divided by 2 is 9. As a check, 7, 8, 9, and then from 9, 10, 11. The triangle is a little trickier. So the centroid of a right triangle is 1/3 of the way up from the bottom. If this is 1 unit in height for the whole triangle, then the centroid is 1/3 of the way up from the base. So it seems as if for the triangle, we have y centroid is y of the base plus 1/3 of the height. So that would be 11 units plus 1/3 of 3 units. So that's 12 units. So here's 11 is the bottom. So the centroid here is at 12 units. So I think I like 4, 9, and 12. Answer C here. Now, what is y centroid for the entire shaded area consisting of the two squares and the triangle together? So let's work that out. It should be the centroids of the individual constituents, each one weighted by its area. So y centroid of the entire shape is y centroid 1 times area 1 plus y centroid 2 times area 2 plus y centroid 3 times area 3 divided by the sum of the three areas. So it's just a weighted average weighted by area. For the biggest shape, we have 4 units times 36 square units. For the middle shape, we have 9 units with an area of 16 square units. And then for the triangle, we have 12 units with an area of 6 square units. And then we divide by 36 plus 16 plus 6 square units. That gives us 6.207 units, which matches answer B, bravo, 6.21 units. And that seems plausible that the centroid is at 6.21 units. So if we had drawn the centroid at 6 units, we would have 30 units of material below the centroid and 28 units of material above the centroid. So the median where half the material is above and half is below, must be just a little bit below y equals 6 units. The average and the median don't have to be at the same place. The median is just easier to estimate in your head. So it works out that the average is a little bit above 6 units, though interestingly the median is a little below 6 units in this case. So the vertical centroid is 6.21 units. So I like answer B here, bravo, 6.21. In class recently you tried one problem similar to this one, but we used metric units because we really prefer metric units. So there was one concentrated load and one distributed load. I think the problem you tried in class had only one distributed load and no concentrated load. And you want to find the support forces at A and at B. I so dislike US customer units, I'm going to pretend that where this diagram says pounds, it really means Newton. And I'm going to pretend where it says feet, it really means meters. So even though pound and a newton are not the same, and a foot and a meter are not the same. Let's just pretend it was labeled in meters and in newtons instead of being labeled in feet and in pounds. So here we go, I've redrawn it. We want to find the support forces at A and at B. So we have a hinge support at A, so there will be a y component and an x component in general, though I think we can see that the x component will turn out to be 0 because there are no horizontal loads. And then at B, we have only a vertical component since that's a roller support. And then 6 meters from the end, we have a concentrated load of 4,000 newtons. I'm going to say 4 kilonewtons. And that is a distance 6 meters from point A. Then we have to replace this distributed load of 500 newtons per meter, which spans a 12-meter length, with the equivalent concentrated load. What does equivalent mean? It means it will get you the same support forces. So a distributed load will not cause the beam to deform under load in the same way as an equivalent concentrated load. Those will turn out to be different answers when we study how the shape of the beam changes as you put forces on it. But for the purpose of determining the support forces at A and at B, you can treat the beam as a perfectly rigid object and replace the distributed load with the equivalent concentrated load. The equivalent concentrated load is the area under this curve. We take 500 newtons per meter and multiply by 12 meters. That's the integral, basically. That will give us 6,000 newtons. And then we put that concentrated load at the centroid. Since this is a rectangular shape, the centroid is just the middle. So the centroid will be 6 meters back from the end, which will be 6, 7, 8 plus 6 is 14 meters over from the left. Let's write that down. So this equivalent concentrated load will go here. Here is 6 meters from the end, although I think we're going to want to measure things from the left end, but it seems like this must be 6 meters from B, since it's half of this 12-meter distance over which this distributed load is applied. And if we call this P for the moment, since P seems to be the symbol used commonly for concentrated loads, P equals 500 newtons per meter. That's this value W, the force per unit length, times the length, which is 12 meters, which is 6,000 newtons, which we can write as 6 kilonewtons. So we'll call that 6 kilonewtons. And this distance is 6 meters, but really we want the distance from A so that we can do torques or moments about A. 6, 7, 8 plus 6 is 14. So we have a 4 kilonewton concentrated load 6 meters from A, and we have a 6 kilonewton equivalent concentrated load 14 meters from A. Just as a double check on our lengths, 14 plus 6 is 20, 6 plus 2 is 8, plus 12 is 20. So I think we got that right. So the sum of the forces in the x direction acting on the beam as a whole just equals A sub x to the right. So there's nothing else to oppose it, so A sub x must equal 0. Then, if we do the sum of the torques, also known as moments, about point A, counterclockwise minus clockwise, well, the only counterclockwise one is B, so we have By, whose lever arm is 20 meters, the entire length of the beam, and then we have two clockwise ones. We have 4 kilonewtons at a lever arm of 6 meters, and then we have 6 kilonewtons at a lever arm of 14 meters. So 24 plus 84 is 108, divided by 10 would be 10.8, divided by 2 is 5.4, so we have 5.4 kilonewtons, and then we can say 0 is the sum of the forces in Y on the beam, and that is AY plus BY minus 4 plus 6 is 10 kilonewtons. So AY plus BY together have to add up to 10 kilonewtons, and BY is 5.4 kilonewtons, so that leaves 4.6 kilonewtons left over. So then we have BY is 5.4 kilonewtons, and AY is 4.6 kilonewtons. Okay, so we have a left support force vertically 4.6 kilonewtons, a right support force vertically 5.4 kilonewtons, and this horizontal support force is 0 since there's nothing else for it to oppose horizontally. So we already did one example like that in class. So this is one straightforward example of using a centroid. You take a uniform distributed load and you use a centroid as the position at which you apply the equivalent concentrated load, and then the area under the curve, which is just, in this case, since it's uniform, it's just this force per unit length W times the length over which it's applied, which is 12 meters in this case, to get the magnitude of the equivalent concentrated load. You can see my math on the next page. I did it using Mathematica and I used US customary units. I didn't pretend it was in metric units, but you see that numerically it's the same values. This next example is a little bit harder because the distributed load is non-uniform. So we have to figure out the centroid of something that's not just a rectangle. So the problem here is to find the support forces at A, where there's just a vertical force, and at B, where in principle there are both horizontal and vertical forces, though you know in practice there will only be a vertical force. Again, since I dislike US customary units, I'm going to pretend where this drawing says feet that it actually says meters, and I'm going to pretend that where it says pounds it really says newtons. So here we go. I've redrawn it pretending that the numbers were actually specified in metric units. So those aren't the same physical quantities, but they're the same numerical values, and I just switched the units from feet to meters and from pounds to newtons. One way we can do this is to break this shape up into one rectangle and one triangle. So here's a rectangle whose height, the whole length of the beam, is 1 kilonewton per meter. So this is 1 kilonewton per meter. And then here's a triangle whose height above the rectangle is 2 kilonewtons per meter on one end and is 0 on the other end. So let's see how that works. So we know, since this triangle on top is a right triangle with its base on the right side here, then 1/3 of the way from the right is where the centroid of the triangle triangle is. So that will be useful. So the centroid of that triangle part is going to be 1/3 of 12 meters, which will be 4 meters from the right side. So again, we'll decompose this funny shape into a rectangle, which is just flat the whole way, and a triangle, which makes up the difference. And it's easy to get the centroid of this rectangle, it's just in the middle, and it's easy to get the centroid of this triangle. Since it's a right triangle, it will be just 1/3 of the way to the left of its end. So in this case, the centroid is halfway across the beam, which is 9 meters from the end. Since this whole width here is 6 plus 12 is 18, so the centroid here will just be half of 18 is 9 meters. And then in this case, this centroid will be 1/3 of the way. So we start at the very end, we go 1/3 of the way back. So this distance is 1/3 of 12 meters, which is 4 meters from the right-hand side. 4 meters from the right-hand side is the same as 14 meters from the left-hand side, since the full length of the beam is 18 meters. So 6 plus 12 is 18, so there's 18 meters. So the centroid of this rectangle is just halfway across, is 9 meters. The centroid of this right triangle is the end minus 1/3 of the way back. So the end would be at 18, and then 1/3 of 12 here is 4, so 18 minus 4 is 14 meters from the left end. Now in retrospect, maybe we didn't have to calculate numbers from the left end because we probably will want to pivot either about the right end or about A. But in any case, okay, I just happened to measure everything from the left end in my initial estimation. Let's also figure out the areas under the curve. So the area of this rectangle is 1 kilonewton per meter times 18 meters, which is 18 kilonewtons. And then the area of this triangle is 1/2 times the base times the height. So that's 1/2 times 12 meters times 2 kilonewtons per meter. So that's 12 kilonewtons total. I think we could check that another way. Let's take the area of this little chunk before the triangle starts. So that's 1 kilonewton per meter times 6 meters is 6 kilonewtons. And then this chunk should have an area which is the average of its height times the length. So the average here is between 1 and 3. The average is 2. So 2 kilonewtons per meter, the average intensity here, times 12 meters is 24. So if 6 plus 24 is 30 total, here we got 18 plus 12 is 30 total. Okay, so we got the same total. That's encouraging. Now let's draw a free body diagram for the beam with the distributed loads replaced by equivalent concentrated loads. We have AY here. We have BY here. We could have a BX here, but we know it will be 0. And then we have 18 kilonewtons in the middle, and we have 12 kilonewtons 4 meters from the end. And I actually think it will be easier for us to measure distances from B rather than distances from A. So if we measure distances from B, this distance is 4 meters, and this distance is 9 meters. And then the distance to A is 12 meters. Okay, let's figure out, I think we can figure out by inspection that the support force horizontally at B equals 0, because B sub x is the only horizontal force. Let's use torques or moments about B to figure out the support force at A. So 0 is the sum, counterclockwise minus clockwise, pivoting about B of the torques, which is, so since we're pivoting about B, these two loads are counterclockwise, and this support force at A is clockwise. So we have 12 kilonewtons times 4 meters plus 18 kilonewtons times 9 meters minus AY times 12 meters. That gives us AY equals 9 times 18 plus 12 times 4, and then all of that divided by 12, which equals 17.5 kilonewtons. And then we know 0 is the sum of forces in Y acting on the beam, which is AY plus BY minus 18 plus 12 is 30 kilonewtons. So the two numbers have to add up to 30, and one of them is 17.5. That gives us BY equals 30 minus 17.5, which is 12.5. So this equals 17.5 kilonewtons, and this equals 12.5 kilonewtons. And I guess if we were going to go draw it over here, we could say this is 0, this is 12.5 kilonewtons, and this is 17.5 kilonewtons. Okay, so we found a 12.5 kilonewton vertical support force at B, a 17.5 kilonewton vertical support force at A, and the horizontal support force is 0 since there are no horizontal load forces. If you look at the next page, you'll see that I did the math in Mathematica in a previous year. I used feet and pounds instead of using meters and newtons, but the numerical values are the same. 17,500 upward at A, 12,500 upward at B. So that is our first use of the centroid concept, is finding the centroid of a distributed load so you can figure out where to put the equivalent point load, the equivalent concentrated load, where equivalent means it will get you the same support forces. Now let's move on to the topic that I call second moment of area, but most architects and engineers call moment of inertia. And this will really help us to understand why this meter stick is about 10 times stiffer when held like a joist than it is when held like a plank. In this set of diagrams, all four of these shapes have the same area. So the area is 24 squares on the graph paper. For each of the four shapes, which one has the largest moment of inertia, which I prefer to call second moment of area. So which one has the largest second moment of area about the x-axis? The x-axis, y equals 0, is right through the centroid vertically of all four shapes. So you know that moment of inertia, or my preference, second moment of area, tells you how far does the material tend to be in some average sense, kind of a more variance-like sense rather than an average-like sense, where we're looking at distance from the x-axis where we contrive to put the vertical centroid along the x-axis. So we position each shape so that its vertical centroid is at y equals 0, and then you say which of these shapes is more spread out in y. And I think you can see by eye that the taller, thinner I-beam with the larger flanges is the one whose material is most spread out away from the x-axis. And then B would be the second most spread out. So this is the I-beam with a somewhat smaller flange, and then some of the material is moved, I guess, from the flange into this webbing area. So see, for B versus A, the flanges are smaller and they're also not quite as far away. And I think I somehow did that just so things come out to be nice numbers of squares on my graph paper. And then here we have two rectangular cross sections, which are less exaggerated but are kind of like this and like this. So it appears that the one with the smallest second moment of area, the one that would make the least stiff beam, is D, delta, and the one that would make the most stiff beam is A, alpha. So this one, A, has the largest second moment of area just by inspection. We'll work out an example in a moment. And this one, D, has the smallest second moment of area. And in fact, they're in order: largest, second smallest, smallest. So in fact, the next slide asks which one is the smallest. Well, the one on the right here, D, delta, is the smallest. So the definition of second moment of area, which is also known as moment of inertia in architecture and engineering, is the integral y squared dA. So we're trying to figure out how far it is above the y-axis. And this is labeled by convention I sub x, which means with respect to the x-axis. If you don't want to use calculus, or if things are nicely broken up into a grid of graph paper, then instead of integrating, you can just sum over small patches. Each patch is multiplied by that patch's area, and then times the square of the distance of that patch from the x-axis. If we were to move the x-axis down by 2 grid units, how would that affect the second moment of area with respect to the x-axis of each of these shapes? And would it affect all of them in the same way? So what we have to think to solve this is the parallel axis theorem. The parallel axis theorem says that if we take a shape that initially has its centroid along the x-axis, so initially the y value of its centroid is 0, and you displace that y centroid to y equals d. So the centroid was at y equals 0, now the centroid is at y equals d, and it's a shape of area A, then whatever value you got for the second moment of area is increased by AD squared. So that's the area times that displacement squared. And this is very similar to the parallel axis theorem we used for rotation, where we had the mass times the perpendicular distance squared. Although one thing that's a little different is for second moment of area for beam shapes, we only use distance in one direction. So instead of the distance out from an axis of rotation that points in and out of the page, instead you have the distance up or down from the horizontal axis. So this distance d is only measured vertically if we're calculating the second moment of area with respect to the x-axis, which is what we will always do for beams. So for all four of these shapes, the area is the same. That was just, we contrived to make the area the same, and we displaced them all by the same distance d, which was 2 units. So we're actually increasing the second moment of area by 24 square units times 2 units, the quantity squared. And by the way, the second moment of area has units of length to the 4th power. So if you're working in centimeters, it's centimeters to the 4th power. If you're working in meters, although meters would be awfully big for the cross-section of a beam, it's meters to the 4th power. If you're working in inches, it's inches to the 4th power, because it's area times distance squared are the units for this second moment of area. Even though the values for second moment of area for these 4 beams are all different, the amount that we increase each one by is the same in all 4 of these cases. In each case, we increase it by this area, which is 24 square units for each of these 4 shapes, times d squared, and the displacement is 2 units in each case. I guess in each case we're increasing it by 96 units to the 4th power. So I like the answer A here. Yes, I sub x would change by the same amount for every shape. It increases by the same 96 units to the 4th power for all 4 shapes, because the area is the same and the displacement is the same. Let's take it as a given that the second moment of area is 1/12 bh cubed for a rectangle of base b and height h. And then let's use the fact that all 4 of these shapes either are rectangles or are composed of rectangles, and this will give us an excuse to try out the parallel axis theorem. And let's actually calculate I sub x, the second moment of area with respect to the x-axis for all 4 of these shapes. And let's see what we get. Maybe let's start with the easy ones. Let's go in reverse order. So we'll start with d. So for d, we have the base is 6 units and the height is 4 units. So the second moment of area is 1/12 6 units, 4 units cubed, which works out to be 32 units to the 4th power. And I think actually on the slide I said use centimeters for the units, so that would be 32 centimeters to the fourth power if we take a unit to be a centimeter. C, Charlie, we just reverse the base and the height. So now we have the base is 4 units, the height is 6 units, so we get I sub x is 1/12, 4 units, 6 units cubed, which is 72 units to the fourth power. Or if a unit is a centimeter, then it's 72 centimeters to the fourth power. By the way, one little digression is if you take 1/12 b h cubed and you divide it by 1/12 h b cubed, which is just what you would get if you reverse the order, after some cancellation, you get h over b, the quantity squared. So it's the aspect ratio squared. So this aspect ratio is 3 to 2. It's 1/2. So the ratio of these two values should be 3/2 squared. So 1½ squared is 2.25, right? Because 15 squared is 225. So in fact, I think if you compare 72 with 32, you'll find that 72 is 2¼ times 32. Sure enough, 72 is 2¼ times 32. So we'll use that fact in the future. If I take this object and compare it this way versus this way, the ratio of the two stiffnesses turns out to be this aspect ratio squared. And actually for this meter stick, that aspect ratio is about 3. So the aspect ratio squared is about 10, 9 or 10. So this is actually 10 times as stiff this way as it is this way. Now let's work out shape B. So we have this shape, and then we have 2 times this small shape, and then we have the area of this small shape times 7½ centimeters squared. And then there are actually 2 of them because there's one on top and one on the bottom. So 2 times that. We have the contribution from this vertical rectangle that is centered at y equals 0. Then we have the contribution from this horizontal rectangle, and times 2 because there's another one. And then we have the fact that this horizontal rectangle has a centroid which is displaced. So we have to use the parallel axis theorem for this one, and then we do it again for this one, which just means multiplying by 2. So this vertical shape is 1/12. It's 1 unit wide, and its height is 15 units. Oh, its height is 14 units. Okay, right. So this thing's height is 14 units. So measuring from the axis up to the centroid of this horizontal piece is 7½ but from the axis up to where this piece ends is, in fact, this is 7, this is 7. So this is 14. If we go from here up to here, that's 14 units. Then we have 2 times 1/12. The width of this thing is 5 units. The height of it is 1 unit. Then we have the area of this little piece. So there's a 2 just because we have 2 of them. And then the area of this horizontal piece is 5 units. It's 5 wide and 1 tall. So there's 5 square units. And then it is displaced 7½ centimeters up. So we should be able to combine all that and get a number. Before we do that, let's work out what the values would be for A. So it's the same process for A, but different numbers. The vertical piece by itself is 1/12, and then the width is a ½ unit. So there's a ½ centimeter. And the height of this piece, so this distance from here down to here would be 16. So this is 16 centimeters cubed. Plus, now we have 2 flanges. Each flange contributes for its own shape 1/12. That's 8 centimeters wide, and it's 1 centimeter tall. Then we have the displacement of the 2 flanges from the x-axis, which is, so it's 2 because there are 2 of them. The area is 8 square centimeters because this is 8 wide and 1 tall. So the area of this horizontal rectangle is 8 square centimeters. And then the distance that it's displaced from the x-axis is 8½ centimeters. We square that. And let's work out all these terms separately so we can see which ones are most important. So I'll do a little bit of math and I'll write down the numbers. The final numbers we get are 1328 for shape A, 792 for shape B. So you see shapes A and B don't look all that different, and yet shape A's second moment of area is almost twice as big as shape B's. And then shape C is 72 and shape D is 32. And the units here are, well, it's units to the fourth power, or if each box is a centimeter, then it's centimeters to the fourth power. So you can see already, since all 4 of these shapes are the same area in cross-section, you can see why an I-beam has the shape that it has. It's because you really want to put most of the material far away where that y-squared factor makes a big difference to make the I-beam as stiff as possible. Now let's see where these numbers come from. For B, the webbing contributes 229, which is about 1/3 of the total. The flanges, if they were centered on the x-axis, would contribute almost nothing, but the displacement of the flanges, the fact that the flanges are 7½ units displaced in centroid from the x-axis, contributes 2/3 of the total second moment of area. That's 562.5. So that's about 2/3, that's about 1/3 of the total, which is 792 centimeters to the fourth power. For case A, which doesn't look all that different from B, but we took this webbing and kind of made it half as wide, and then we pushed the flanges out a little bit and we made them bigger. So you can see that the webbing in this case contributes 171 out of 1328. So what's that, about 15% maybe. The flanges, if they were centered on the x-axis, would be tiny, again about 1 unit, but almost all, so it seems like about 80 or 90% of the total comes from the displacement of these flanges away from the x-axis. So it's 1156 out of a total total of 1328 just comes from the fact that the centroids of these things, each of which has 8 square centimeters of area, are displaced away from the axis by 8.5 units. So this is kind of an illustration of why an I-beam has that eye-like shape. This quantity, second moment of area, which is proportional to the stiffness of a beam, is much, much bigger for the same amount of material if you put it in this I-beam shape. And even more so if you put more of the material into the flanges and not so much into the webbing. To recap on the next few slides, we did the two rectangular shapes first because they were quick. We were just given the formula 1/12 bh cubed, which I'll show you in a moment how to derive with calculus. Then the trick for the non-rectangular shapes was to use, and this is in Onouye Kane section 6.3, the parallel axis theorem, which says, okay, you take the shape as if its centroid were at y equals 0, and then you add to it its area times the square of its displacement from the x-axis. And each one of these sums is over the simple shapes that compose the big shape. So we have bh cubed over 12 for each rectangle, and then you take each area times its vertical displacement squared. And you saw me do that. The way the math worked out for shape C and D was like this. For C, the base was 4 centimeters, the height was 6 centimeters, and we just took 1/2 bh cubed. Likewise for D, so we got 72 centimeters to the 4th power for C, and we got 32 centimeters to the 4th power for D. And I pointed out that it's the same shape but rotated, and the ratio of these two values is this aspect ratio squared, because you take bh cubed, and if you divide that by hb cubed, you just get h over b, that quantity squared. In case you want an independent copy of the math for B, here it is on this page, and here's an independent copy of the math for cross-section A. So each of these 4 shapes had the same area, 24 square centimeters, but the second moment of area was 1328 centimeters to the 4th power for A. It was 792 centimeters for the 4th power for B. It was 72 centimeters to the 4th power for C, and it was 32 centimeters to the 4th power for D. Again, that shows you the motivation for the I shape of an I-beam to get a large second moment of area. So the deflection of a beam under load, for a given load, the deflection is inversely proportional to this second moment of area. Or another way to say it is that the stiffness of a beam is proportional to this second moment of area. So that I-beam shape gives you a much larger stiffness than just an ordinary rectangular shape of the same area. By the way, let's figure out where that 1/12 bh cubed came from. So we'll take y equals 0 here, and then let's consider one little chunk whose height is dy and whose width is b. So we have dA equals b dy, so because this little area has a width of b and a height dy, and then we want to integrate, this is I sub x is the integral y squared dA, and the limits here are from, this is minus h over 2, this is plus h over 2, so here's minus h over 2 to plus h over 2, and that's the integral minus h over 2 to plus h over 2 y squared b dy. B is just a constant, so this is b times y cubed over 3, evaluated from minus h over 2 to plus h over 2, so that's b over 3, here we'll say y cubed for minus h over 2 to plus h over 2, so that's b over 3 h over 2 cubed minus h over 2 cubed. That's bh cubed over 12. We did it. So a little bit of calculus, you can see where that comes from. And on the next page, you have my pre-written math for the same thing. That was our whirlwind tour of chapter 6 of Onouye and Kane on cross-sectional properties. So now we'll move on to talking about beams. So this sort of begins Onouye chapter 7. So this idea of second moment of area, we can file it away for the moment. It will return a little bit later. For the moment, I want you to consider what happens, for example, if somebody stands on the end of a diving board. So in this diagram, we have a cantilever, like a diving board, of length L, and at the far end, there's somebody, let's say there's somebody standing there whose weight is P. So P is the symbol usually used for a concentrated load or a point load. So there's a concentrated load P, okay, like a weight P, point-like, at the far end of this cantilever. Cantilever is sort of like a diving board. And one result of that is that this cantilever, kind of diving board-like shape, is going to bend into a curved shape. So I could do this better with a plastic meter stick, but with this wood meter stick, if I pretend this end is fixed to the wall, and then pretend that I'm standing on this end, when I stand on this end, so the end that's fixed to the wall isn't going to move, but when I stand on this end, this cantilever will bend into a curved shape. And one thing that's interesting to ask is how much is that far end displaced as a function of how long the beam is, and as a function of how much weight I put on the end of the beam, and as a function of what kind of material I make this out of. Is it wood? Is it plastic? Is it steel? And as a function of what is the cross section. And I think you already can and envision that if I were to apply that same force to the end when it's held like this, it would not bend nearly as much. In fact, it'll bend about 1/10 as much if I apply that same force to the end when it's oriented like this versus like this. To start to answer questions like that, we want to ask, what are the internal forces and the internal torques, and we often call torques moments in this context. What are the internal forces and the internal moments in a beam? And in the case of a cantilever beam, like a tree branch, you say, okay, here is my tree branch. Maybe the trunk of the tree is here, and that's the far end of the tree branch. You say, well, suppose I take a saw and I start cutting here, and you're sitting out at the end. Well, you know if I get all the way through, you're going to fall to the ground because somehow the near side of the branch is holding up the far side. So the near side of the beam is somehow holding up the far side of the beam. So it's not hard to believe that to keep the far side of this cantilever up, the near side has to exert an upward force on the far side. And then consequently, the far side exerts a downward force on the near side. And of course, the tree trunk or the wall exerts an upward force at the base and the very near side. But it's actually not sufficient for the near side to exert just a force on the far side. The near side actually also has to exert a torque on the far side. So if you imagine that here, let's just suppose now that my arm is the near side of the beam and this meter stick is the far side of the beam. If I only exert a force but not a torque, then I can, hold the end of the beam up in the air, but I can't prevent it from rotating so that its orientation is like this. So to do that, I actually need to exert not only a force but also a torque. So here I am, I'm the near side of the beam. Not only do I need to exert an upward force to keep this from just dropping, but I also need to exert a torque that goes this way. So the near side needs to exert on the far side a torque that goes this way so that the far end of the beam doesn't just flop over like this. It has to stay out. So there's actually, if I were to cut the beam here and say, what does this side do to this side exerts an upward force on this side, and this side also exerts a torque like this on this side. So we want to be able to study both that force and that torque as a function of length along the beam. And the two most common cases we'll consider are a cantilever, which is supported by being built into a wall on one end. So here's a connection to a wall, and the rest of it is just hanging in the air. And then the other most common case is a so-called simply supported beam, where you just have a single support under each far end. And by convention, so that you get three unknowns to solve for using statics, you have a hinge support on one side and a roller support on the other. Although in most cases, all the loads are vertical, so it's really just one vertical force on one side and one vertical force on the other side in the most common case. So to analyze, if we were to section the beam here, you could say, what does the left half have to do to hold up the right half? That sounds a lot like the kind of analysis we did with trusses with the method of sections, where we said, okay, if we are to cut the truss in half here, we can ask now, what does the stuff that we erased have to do to hold up the stuff that we didn't erase? So we'll ask a similar question. We'll say, what does the left side of the beam have to do to hold up the right side of the beam? And in general, there will be both a force and a torque. And the torque we call a bending moment. So when you say, what force does the left side have to exert on the right side to hold it up? We usually call that the shear force, because you could argue that it's kind of preventing one side from shearing with respect to the other. Although we will also later see that inside the beam there are shear stresses that are proportional to this thing we're calling the shear force. And then we will see that the torque that one side has to exert on the other to hold it up is called the bending moment. So the bending moment through this section of the beam is, what is the torque that this side of the beam has to exert on this side of the beam to maintain the beam's orientation, to hold it up, to keep it in equilibrium. So we're basically going to spend a chunk of time now sectioning a beam and using reasoning, which is analogous to the method of sections, to say what force and what torque does one side of the beam have to exert on the other side of the beam to keep it in equilibrium. So here we go. So when we analyze the forces and torques that act on the beam and that act along each section along the length of the beam, we start out by drawing what's called a load diagram. A load diagram is basically an extended free body diagram for the beam as a whole. Once we have our load diagram, then underneath that we draw a shear diagram. The symbol for shear is a capital V, and that essentially is asking what force does the left side of the section have to exert on the right side of the section to hold it up. And then below that we draw the moment diagram, capital M, which is basically asking what torque does the left side of the section have to exert on the right side of the section to hold it up. And we have some funny sign conventions here. So the sign convention for the shear, which is a capital V, is that V is bigger than 0 when the left-hand side of the section is pulling up on the right-hand side. And the sign convention for the moment is even weirder. The sign convention for the moment is that M is positive when the beam is smiling and M is negative when the beam is frowning. And Professor Farley likes to say, a positive moment makes the beam smile. We're going to see all this in numerous examples, so don't worry if it's a little bit hard to absorb on the first statement. Another way to state the sign convention for this force, V, that the left side of the section has to exert on the right side of the section is, the V is the running sum upward minus downward of all forces exerted on the beam from the left side up to and including X. And we're going to go as a function of X along the length of the beam. So here is our cantilever of length L. So there's the cantilever beam, and I guess I can just indicate that the length of this thing is L. This is X equals 0, this is X equals L, and then we can somehow indicate that this thing is attached rigidly to the wall. So you could draw the wall like that. But in fact, we know that there is a concentrated load P at the end, at the far end of the beam. So we can deduce that there must be an upward support force of the same magnitude, P, exerted by the wall on the beam to hold it up. And then also you know that this is going to cause this thing to try to rotate clockwise. So you must have some torque exerted by the wall on the beam at the place where the beam is attached to the wall to counteract this torque. And in fact, this torque will be a bending moment whose magnitude is P times L. Because if we take this as a pivot, then this is a force P times a displacement L. So this will end up having to be P times L exerted at the left end of the beam to keep it from tipping over. So this load diagram is basically an extended free body diagram for the beam. I think I should have written EFBD here instead of FBD, although Onouye calls this an FBD. And then after that, we're going to draw the shear diagram, which is a diagram of forces exerted by one side on the other, where what do I mean by one side? I mean as if we were to cut the beam at position X with respect to the left-hand side. What does the left side have to do to keep the right side up? So the left side has to exert some force on the right side, and the left side has to exert some torque on the right side. So that force is what we draw as a function of the section point X on the shear diagram, capital V, and that torque that the left side has to exert on the right side is what we draw as a function of the cut line X on the moment diagram M. And this is, again, easier to understand through examples, I think. The little slash mark through this force line means it's a reaction force. In other words, it's not a load that is the beam's raison d'etre. It is a force, or in this case, a moment or torque exerted by the wall or exerted by the support needed to hold the beam up. So this load is what the beam is holding up, and then these so-called reactions, the reaction force, the reaction moment, are what is needed by the rest of the structure to hold this beam up. So the rest of the structure, in this case the wall that the cantilever is attached to, has to exert this upward force, and it has to exert this counterclockwise moment. So the first thing we drew, which we call the load diagram, is basically just an extended free body diagram for the beam showing all forces and torques acting on the beam, and that includes both the loads, which are the beam's job to support, and the support or reaction forces and torques, which is what the rest of the structure has to do to hold this beam up. The next part of this diagram is called the shear diagram, which is this quantity V as a function of X. So here's X, this is X equals L, this is X equals 0. So this is, you could call it V, sometimes people write shear, I think you can write V, so it'd be V as a function of X. And here is plus, here's minus, here's 0. And qualitatively what you're saying is what force does one side of the cut. So you imagine, so as a function of X, like suppose we say this value over here, this is like a quarter of the way across. So then you're saying, okay, if I cut the beam a quarter of the way across, what force does the left side have to exert on the right side to hold it up? And the sign convention is such that if the left side has to exert an upward force on the right side, then it is positive. Another way to say it is that it's the running sum, up minus down, of all forces on the beam up to and including X. So it's from X equals 0 up to X equals X. In this case, this takes a pretty simple form because anywhere we cut this from here over to here, let's say even from here over to here, you know the left side just has to exert a force of P upward on the right side because we have this downward force P at the very end. So in this case, we have this value is P. So it's positive the whole way, and it just has a value of plus P. So along the entire length of the beam, from a fraction of a millimeter past 0 up to a fraction of a millimeter short of L, the force that the left side has to exert on the right side is P upward. So this is a pretty simple function of X. From 0 up to L, it just equals positive P. And the same thing is drawn down here on the slide. Next, we ask, what torque does the left side have to exert on the right side to keep it in equilibrium? And that's this moment diagram, M. So we'll see whether it's positive or negative, but it has kind of a funny sign convention. So first of all, if you say, what torque does the left side have to exert on the right side? If you go right out to here, then there's basically a negligible torque. It's just this force P, but there's no lever arm. So it's just a negligible torque. But then it gets bigger and bigger and bigger because the lever arm gets longer and longer until you get to 0, and then the torque is P times L here. So it seems like the magnitude should be 0 here, and the magnitude should be P times L here. But what's the sign convention? Well, this beam is frowning, so the sign convention will be negative because a positive moment would make the beam smile. So in fact, what we get is a curve that has a constant slope, so it's a linear curve, and this value is minus P L. So there's the moment curve. And you can see the same thing in the slide, and then I'll give you also the easier to read version of the slide. So that's what the diagrams look like for a cantilever, which on the left side is attached rigidly to the wall, and on the right side has a concentrated load, which is a force of magnitude P. This will all be really mysterious to you right now, but after a couple more examples, it might start to make sense. Next, let's try a mirror image of that same cantilever beam. So the load diagram is just an extended free body diagram of the beam. We have the load P over here, and then we have the reaction force P over here exerted by the wall, and then this load creates a counterclockwise moment, so we need a clockwise reaction moment over here, and this is X equals 0, and this is X equals L. So next, let's draw the shear diagram, and positive, negative, 0. Here's the x-axis, so here's x equals L. And running some up minus down, up to and including x of forces. So we have a down, and then we have nothing, and then we have an up. So this will look like this. It is negative up until x equals L, and it comes back to 0. Seems like it's convention to fill this in so it's like a solid shape. So this is minus p. So there's the v versus x function. It's basically just a constant value of minus p. Minus p is the point concentrated force you put at the end of the cantilever. In this case, it's the left end, and the right end is supported by the wall. Then we have the moment diagram. So here is plus 0 minus. This is the bending moment as a function of x. And here is the x-axis. And the bending moment has to be 0 at the very end. So anytime you have a free end or even a simply supported end, the torque at the end has to be 0 because this end, whatever the support condition at the end, here it's just flopping, so there's no torque exerted at the very end. And even if it's just sitting on top of a roller, or if it is supported by a hinge, there's still no torque there. So the moment is always 0 at a free end or a roller end or a pin/hinge end. But the moment is non-zero in general at the fixed end of a cantilever, for instance. So the slope of the moment curve equals the shear curve. This is called shear, this is called bending moment. So we want a curve whose slope is minus p. So that would be a first order polynomial sloping downward, but we want it to be non-zero on the right and 0 on the left. So we'll start at 0, and then we will slope downward like that. And then we'll draw it shaded in, which seems to be the convention. And this value is minus PL, because this is a slope of minus p over a distance L. And I guess if I wanted to be a little more careful, I can make sure that this nicely lines up with x equals L. Okay, so that should be the moment diagram. And I guess we can check the beam is frowning, so the moment should be negative. A positive moment makes the beam smile. Let's see whether that agrees with Onouye's solution. So their load diagram looks like ours, their shear diagram looks like ours, and their moment diagram also looks like ours. So it seems like we got the right diagram. So remember, the sign convention is v of x. The shear diagram is positive when the beam to the left of x is pulling up on the beam to the right of x. I find the way I wrote it up above easier to remember. And then m of x is positive, the moment is positive when the beam is smiling. A positive moment makes the beam smile. So the transverse shear, I like this better actually, the transverse shear, v of x, is the running sum of forces acting on the beam from 0 up to x, where upward is positive. So then you can clearly see that it should be negative p from 0 until just before L, and then once we get past L, it basically goes back to 0. And the bending moment is the torque exerted by each side of the beam cut at x. You cut the beam at x, you say what torque does one side have to exert on the other, but you have to be careful of the sign convention. The easiest way to remember the sign convention is a positive moment makes the beam smile, but computationally the easiest way to remember the sign convention is that the shear diagram equals the slope of the moment diagram. So the v diagram is the slope of the m diagram. So if you know the v diagram, you can say, okay, what diagram would have a slope equal to v, but then there's still an undetermined constant, right? If you integrate, there's always an undetermined constant, and that constant is determined somehow by the conditions at the end. For example, a free end or a simply supported end has no torque exerted on it. There could be a force at a simply supported end, but no moment. And then at a free end, there can't be either a force or a torque. What that means is, you see, here's my cantilever beam. At this end, there's both a force and a torque. At the other end, there's neither a force nor a torque. But if I hold the beam up like this, then on both sides there's a force, but neither side can exert a torque. Let's do a few more examples of these shear and moment diagrams just to make sure we've got it, and then we'll change gears a little bit after that. So here is a simply supported beam. That means it has one support on each end, and by convention one of them is a roller support, the other one is a hinge support. Let's try drawing the load diagram, the shear diagram, and the moment diagram. Here we go. This beam is labeled with the loads in thousands of pounds. The K means kips, those are kilopounds. Richard Farley laughs when I say kilopounds, but the K is for 1,000, and it's 1,000 pounds. And then the little tick mark means feet, so it's thousands of pounds is what a K is, and then the little tick mark means feet. I'm going to pretend it's labeled in metric units. So when I see K, I'm going to interpret it to mean kilonewtons, even though that's not what the author intended. And when I see the little tick mark, I'm going to interpret it to mean meters. So I'm going to draw my diagram as if everything were in metric units. So here we go. So here's my interpretation of the drawing. We have point A pin support, point B, a roller support. So this combination is called simply supported. And then there's a single 10 kilonewton. It's 10,000 pounds in the original diagram. I'm going to call it 10 kilonewtons. So it's a 10 kilonewton concentrated load, 6 meters from A and 4 meters from B. So the total length of the beam is 10 meters. And again, of course, originally it was feet. I'm pretending feet are meters. So notice you have to know what the support forces are before you begin. And since there isn't an obvious symmetry, we have to work them out. So at this pin support, there is a vertical support AY, and there in principle could be a horizontal support AX, although that's always going to be 0 in our beam loading diagrams. Usually we only consider vertical loads on these diagrams. And then over here at B, we have only a vertical force. So here's BY. So AX will be 0. So we need forces forces AY and BY, which add up to 10 kilonewtons. And you could guess, I guess, that they're in the ratio of 4 to 6 and that this one has to be bigger. But let's just do it. So we'll say 0 is the sum counterclockwise about A of the torques or moments. So about A, pivoting about A, counterclockwise we have B sub Y times 10 meters. That's counterclockwise. And then clockwise we have 10 kilonewtons times 6 meters. So that gives us BY equals 10 kilonewtons times 6 meters divided by 10 meters equals 6 kilonewtons. And then you know that AY is 10 kilonewtons minus BY, but we can write it more formally. So 0 is the sum of the forces in Y acting on the beam, which is AY plus BY minus 10 kilonewtons. That gives us AY equals 10 kilonewtons minus BY, so that must be 4 kilonewtons, which is exactly what Onouye drew down below, except that he drew thousands of pounds. So this is 4,000 newtons and this is 6,000 newtons. Okay, now let's redraw that in the form of a load diagram. So I will draw the beam up here. We're going to call this LOAD. We have a reaction force here, which is 6 kilonewtons, and we have a reaction force here, which is 4 kilonewtons, and we have a concentrated load here, which is 10 kilonewtons. And then we can mark some distances, some dimensions. Let's draw some dimension lines. So this is 6 meters, and this is 4 meters. That's our load diagram. Then let's draw our shear diagram. So we have a vertical axis, positive, negative, 0. Here's the x-axis. So this is x equals 0. This is x equals L. And the shear is the running sum up minus down of all forces on the beam vertically from 0 up including x. So here is plus 4, and now plus 4 minus 10 is minus 6, and then we go back to 0 over here. See, and then this is, I guess, where the shading comes in, so you can tell what part is positive and what part is negative easily. So this is plus 4 kilonewtons, and this is minus 6 kilonewtons. Then we have the moment diagram, plus 0, minus, here's the x-axis, so this is m. M is the bending moment. A flat value is a 0-degree polynomial, so the bending moment will be a 1-degree polynomial. You integrate a 0-degree polynomial, you get a 1-degree polynomial. So we have a first-degree polynomial. So we want a curve whose slope is plus 4 kilonewtons, and the moment has to be 0 at both ends because the supports at the end of a simply supported beam do not exert any torque. If you have like this built into the wall end of a cantilever, that exerts a torque there, but these supports don't exert any torque. So we have a slope of plus 4 kilonewtons, and then we have a slope of minus 6 kilonewtons, and it should come back down to 0, and that makes sense. You have a slope of plus 4 for a length of 6, and you have a slope of minus 6 for a length of 4, so that adds up. So this is slope equals minus 6 kilonewtons. And then by convention, you usually indicate the value of largest magnitude of the bending moment, because that will turn out to be related to certain beam design criteria. So what is the largest value here? So this happened at x equals 6 meters, so 4 kilonewtons times 6 meters is plus 24 kilonewton meters. Yeah, so by convention, you mark the largest magnitude bending moment on the diagram so that you know what it is. So the largest value here is 24 kilonewton meters. Remember, torques, normally the SI unit for torque is the Newton meter, but we're dealing with things that are kind of the ton scale, so kilonewton meters is our unit for torque on these diagrams. So I think that's good. Let's compare with Onouye's solution. Okay, cool. It looks as if Onouye agrees with us, although we pretended his drawing was in metric units. Notice, right, the shear diagram, V of x is the slope of m of x. Over here, this shear value is the slope of this curve, and this shear value is the slope of this curve. And then you have to be careful that the m value is 0 at each end, unless the end is a special kind of end that can exert a torque, like the built-in fixed end of a cantilever. And then he wrote 4,000 pounds, 4 kips here, which would make sense if we were using those units. And he wrote minus 6 kips here, which would make sense if we had interpreted the units to be those dreadful US customary units. And then he wrote 24 kip feet, and we wrote 24 kilonewton meters. Good. So I think we are good here. Okay, let's try drawing the load, the shear, and the moment diagrams for this simply supported beam. So it has a pin support on the left side. It has a roller support on the right side. It is 15 meters long, and there's a 10 kilonewton load 1/3 of the way across, and there's another 10 kilonewton load 2/3 of the way across. So this is 10,000 newtons. This is 10,000 newtons. And then these are placed symmetrically. So the two support forces have to add up to 20, and they're symmetric. So each support force must be 10. So we don't even need to do the math there because we can figure it out by symmetry. So that's our load diagram. Then we can draw the shear diagram, plus 0, minus, here's our x-axis, here's the shear diagram, running sum up minus down from 0 up to x. So we abruptly go up to plus 10 here, and then we go from plus 10 down to 0, we stay at 0, and then we go down to minus 10, and then we come back to 0. So this is plus 10, this is minus 10 kilonewtons, plus 10 kilonewtons. So that wasn't too bad. Then we can draw plus 0 minus our x-axis. This is the bending moment. So we want the curve whose derivative is this curve. We start out at 0 because it's a simply supported end. So we have a positive slope here, and then we have 0 slope here, and we have a negative slope here. Then this just fills in the area down here. And this flat plateau is so here's 10 kilonewtons times, oh, I forgot to write the distances, duh. Okay, so this and this is 5 meters, this is 5 meters, and this is 5 meters. So 10 kilonewtons times 5 meters is plus 50 kilonewton meters. Okay, so I think that is our solution. And I imagine Onouye has a solution we're going to compare with. Okay, cool. In this case, we're comparing with my solution, not his. So we have the 10 kilonewton upward support force on the left, and then 5 meters over from there, we have 10 newton load downward, 5 more meters, we have 10 kilonewtons down, 5 more meters, we have the plus 10 kilonewton support force on the far right end of the beam. So we have this positive 10 kilonewtons in this region, the left 1/3, and then this is 0, and then we have minus 10 kilonewtons down here. And the moment diagram slopes up linearly, stays flat, slopes down linearly. It's positive. A positive moment makes the beam smile, and it is plus 50 kilonewton meters. And you can see, you can sort of imagine the beam smiling because there's something pushing it down in the middle, and there's something pushing it up on the end. So I think that makes sense. So the beam is smiling. I think we have one more example. But first, to summarize, just to recapitulate a little bit what we've been doing here. So the shear V and moment M diagrams. First, you draw a load diagram. The load diagram is an extended free body diagram that shows all of the vertical forces acting on the beam. So for example, we did that here. The shear diagram, V, graphs the running sum of all vertical forces, both supports and loads, acting on the beam from the left side up to X, where upward is positive and downward is negative. So there you go. So you start at 0 and you go up to point X, and up is positive and down is negative. And it's just the running sum, starting at 0, ending at X. Draw the moment diagram. You notice that V is the slope of M. So V of X is d by dx of M of X. So you're basically integrating this curve, but you have to figure out where the offset is to your integral. So the change in the moment from x1 to x2 is given by m2 minus m1, that's a change in moment, is x2 minus x1 times the average of V. That's another interesting trick. We're going to use that trick, I think, in the next example. So you see this difference here is the distance in X times the average value of the shear diagram here. And then this change, you see the average is 0. So that makes sense, the change is 0. And then here the average is minus 10. So this change from here to here is minus 10 times this distance, which is 5 meters. So that makes sense. It's a change of minus 50 kilonewton meters. Okay, so this is basically just the definition of how you do an average in calculus with integration. If the end of a beam is unsupported, in other words, it's free, it's just waving in the air, or if it's hinge or pin supported, or if it's roller supported, then the moment has to be 0 at that end. So normally moment is 0 at the end. The exception is you can only have m not equal to 0 at an end if the support at that end is capable of exerting a torque on the beam. For example, the fixed end of a cantilever has m not equal to 0. Okay, for our next example, let's try drawing the shear and moment diagrams for this simply supported beam which has a uniform distributed load. So we haven't done that before. So we have a uniform distributed load. So there's a 5 meter length of this beam. So this entire length is 5.0 meters. And then we have a uniform distributed load of 3 kilonewton per meter. So we're going to say, here we'll just draw this huge number of little arrows. So then we kind of enclose it with this shape here, and we say W equals 3.0 kilonewtons per meter. Okay, now you actually do not want to erase this, but to solve for the support forces, you have to figure out what the equivalent concentrated load would be. Sometimes you can do it by inspection. Well, here, let's just draw a little copy over here. So if we draw a little copy, see the equivalent concentrated load would be, that's 3 kilonewtons per meter times 5 meters equals 15 kilonewtons. So we have 15 kilonewtons, and the centroid is right in the middle of the beam. So that means our two support forces, notice we have a single vertical support force at each end. At A, in principle, we could have a horizontal support force also, but for these diagrams, that always equals 0. So you know we're going to have 7.5 kilonewtons on this side and 7.5 kilonewtons on this side because it's a symmetric situation and the two support forces have to add up to 15. So we can draw over here a reaction of 7.5 kilonewtons, and we can draw over here a support reaction force of 7.5 kilonewtons. So this is our load diagram. Then we can do some erasing and draw our shear diagram. Our shear diagram will have a vertical axis, which could be positive, 0, negative, and here is the x-axis, and this is V, which is the shear, and it is the running sum, up minus down, of everything acting on the beam from 0 up to x. Start out at x equals 0, you have plus 7.5. So here is plus 7.5. It's really a vertical straight up. And then we have a downward slope of 3 kilonewtons per meter. And then you know what's going to happen on this end is you're going to be at a point where 7.5 brings you back to 0. So we really have, on this end, we're going to have minus 7.5, and it's going to pass through 0 in the middle. Okay, so this is slope equals minus 3 kilonewtons per meter, and this value is plus 7.5 kilonewtons, and this value is minus 7.5 kilonewtons, and we can fill this in like this. And this really is a vertical line. This really is a vertical line. That's the shear diagram. So this is different. So now our shear diagram is a first degree curve. So our moment diagram will be a second degree curve, which is a little bit trickier to draw. Plus 0 minus. The simply supported beam smile miles. So I guess we expect a positive moment. So here's m. That's the bending moment. So it's going to be 0 on the ends because they're simply supported ends. So we have a curve whose slope will be plus 7.5 over here. Its slope will be minus 7.5 over here, and its slope will be 0 in the middle. So that's basically a parabola like this. Notice this looks exactly like the velocity versus time curve for a ball thrown straight upward, and this looks like the position versus time curve for a ball thrown straight upward. If you take a ball and you throw it straight up in the air, this is like y versus time, and this is like v sub y versus time. So we can fill this in, and then you say, well, what is the maximum value? Well, here's where it really helps to use that rule. So we can say m2, so this point here, this is basically my point 2, and this will be my point 1. m2 minus m1 equals x2 minus x1 times the average value of v from 1 to 2. This is going to be tricky to follow. The average value of v in this region is 3.75 because we start out at 7.5, we go down to 0. So this difference in x is 2.5 meters. These numbers I chose for this problem were not great. So this because it's halfway across a 5 meter long beam, so it's 2.5 meters. And then this average value of the shear from here up to the middle is plus 3.75 kilonewtons. So when you multiply that together, you get 9.375 kilonewton meters. So this maximum value here, m max, is plus 9.375 kilonewton meters. And you actually want the absolute maximum. So if it were negative, you'd want the largest negative value. I wonder if this will agree with my earlier calculation. Oh, so there's, I guess I had a load diagram already, and usually you only bother with the vertical support forces. Okay, so that load diagram looks like the top. And then qualitatively, we have something that looks like the vertical velocity curve for a ball thrown straight upwards. And here, this looks like the vertical position versus time for a ball thrown straight upward. And then I think I even put numbers on the next page. This is plus 7.5 kilonewtons, as we wrote here. This is minus 7.5 kilonewtons, as we wrote here. And this maximum moment is plus 9.375 kilonewton meters. And we use the fact that m2 minus m1 is x2 minus x1 times the average of the shear diagram from x1 to x2. This is just calculus. This is like the average value of a function over some interval equals the integral divided by the distance. So I think we got that one right. Now, believe it or not, as if this weren't already complicated enough, there actually are two more diagrams you can draw underneath the load and shear and moment diagram. So there's a load diagram on top, which is just a free body diagram. And then there's the shear diagram below that, which is basically just the running sum of forces from left to right. And it basically tells you if you cut the beam at this value of x, what is the size of the force that one side has to exert on the other to keep both sides in equilibrium. And then the moment diagram is the integral of the shear diagram. By the way, this shear diagram is the integral of minus the distributed load. If you look at this w of x, this shear diagram is actually the integral of minus w of x. And that's because, the distributed load points down. If you put a uniform load on a beam, it's a load pointing downwards. So that's why positive value of w of x gives you a negative value of the shear diagram, because w of x is a downward load. Okay, below the shear diagram, you draw the moment diagram, which is telling you the magnitude of the moment diagram at position x is saying how big is the torque. If you cut the beam in half at x, how big a torque would one half have to exert on the other half cut at that value of x to keep everything in equilibrium. So to go from the load to the shear, assuming it is a distributed load, you're basically integrating, although it's negative the integral in that case. To go from shear to moment, you're integrating. And then it turns out you can integrate one more time and you get this thing called the angle. It's like the slope of the beam. So this is 0 slope, and then here's a negative slope, and here's a more negative slope. Or if we bend it like this, you can see that the slope starts out 0 and gets more and more and more negative. So that's the slope diagram. And then finally on the bottom there is the deflection diagram, which is like what is the deflected shape of the beam. So you see this thing is deflected downward in the middle. So it's deflected downward in the middle. Or a cantilever is deflected downward at the end. So it's saying when you stick the weight on the beam, how does the shape of the beam change? So you integrate the moment once more to get this angle, and you integrate that angle once more to get this deflection. So what we're going to do in the next video is to argue why it makes sense that integrating this moment diagram 2 more times gets you the shape of the deflected beam. Because right now you have no reason in the world to believe that that's true. But it turns out if you take this moment diagram and you integrate it 2 more times, you get the shape of the deflected beam. So that'll be an interesting fact that we can look at in the next video. So again, this load diagram is just basically an extended free body diagram for the beam. And then this shear diagram turns out to be the integral of minus the load diagram. We said it was a running sum, and running sum kind of is the same thing as integral. And we said up minus down, and you see this uniform distributed load points downward. That's why you're integrating minus w. And then you integrate the shear diagram, you get the moment diagram. And then, okay, you're gonna have to take my word for it for now. We'll prove it next time. Then you integrate this moment diagram, you get the slope, which is, this is how different from horizontal is the tangent line of the beam at x. And then you integrate that 1 more time, and you get how far deflected from flat is the beam at that value of x. So it's going to take us some work to get from here down to here, but it could be kind of fun. So you might ask, why do we care about these crazy beam diagrams anyway? I mean, what is the point of drawing these diagrams showing the shear and the moment as a function of length along the beam? Well, it turns out if you look at the way a wood frame house is built, for example, you have like some big beams on the end, and then you have some floor joists running from from end to end. And you might say that this whole floor has to support some number of newtons per square meter, or in the US, some number of pounds per square foot. And then when you divide that by the distance between adjacent floor joists, that gives you some number of newtons per meter along the length of a joist, or some number of pounds per foot along the length of a joist. And then you want to decide then, when you build the floor, what size dimensional lumber do you put underneath the floor? Do you use 2x6s, 2x8s, 2x10s, 2x12s in common US dimensional lumber numbers? And part of that depends on how long the beam is, and part of it depends on how much weight per unit length it has to support, and part of it will depend on the properties of the wood that the joists or beams are made of. So the floor of a structure has to carry some specified weight per unit area. So then the beams must be strong enough to support this load without failing, and they also must be stiff enough to support this load without excessive deflection. So if you walk on the floor and it sags, a centimeter, that's uncomfortable, and it might damage a plaster ceiling down below. So we will pick up in the next video by talking about beam criteria, and I have it here in simpler language. So if you imagine, not so unrealistically, that a wooden beam is a bunch of long parallel fibers that are glued together. If you cut apart a tree branch, or if you cut apart a long 2x4, you can see that. You can see the grain of the wood. So just imagine a wooden beam is a bunch of long parallel fibers that are glued together. Well, the axial stress, that's like how much you're trying to elongate or squish each fiber, can't be so big that individual fibers will snap like guitar strings or crush like a cardboard box. So the axial stress, like how much you're trying to stretch or squish the fibers, is biggest where this bending moment is biggest, we'll see. And it turns out it's biggest at the fibers that are farthest away from the neutral surface. And one way you can see that that makes sense is if you take this, you notice this bent shape, the top is in tension and the bottom is in compression. Well, the top, the very top is the part that's most stretched, and the very bottom is the part that's most squished. So it's the parts that are most stretched or most squished that experience the largest bending stress. So that bending stress is largest, that axial stress of the fibers, also known as normal stress, is largest where this bending moment is largest, and it's largest at the fibers that are farthest from the neutral surface. The neutral surface, if you bend a beam like this, and I think I'll have a better prop next time, then it turns out that about halfway down there is, the top stretches and the bottom squishes. Well, about halfway down there is a plane through the middle of the ruler that doesn't stretch or squish. That's called the neutral surface. And then the shear stress. A lot of people asked about shear stress when we read John Coley's chapter. The shear stress can't be so big that the glue fails to prevent adjacent fibers from sliding parallel to one another. So if you imagine all these fibers next to each other, imagine if you take a deck of cards and you bend it like this, you see the cards trying to slide past one another. So if you put a bunch of glue between your deck of cards and then you bend it like this, then you can see if you bend it too much, the glue fails. So you don't want the shear stress to be so big that the glue fails to prevent adjacent fibers from sliding past each other. So the shear stress turns out to be largest where this shear diagram is largest. And actually, one thing that's surprising is that it's actually largest near the neutral surface. So we'll see that very briefly next time. That's a little bit of that's a detail that's slightly beyond our scope, although I do prove it in the equation sheet. So those above two criteria relate to the strength of the material. In other words, it's like, is it strong enough to resist snapping, irreversible damage? There's a third criterion which will relate to how stiff the beam is. When you walk on the floor, you don't want it to bounce so much that it's uncomfortable. So if the beam bows into a curved shape like this, a smiley face shape, then if that's excessive, then plaster ceilings will crack and floors will feel uncomfortably bouncy or uncomfortably sloped. So it turns out that building codes specify maximum deflections. Okay, so Professor Farley points out that usually you figure out how big, how tall a floor joist you need to get the desired deflection criterion. It turns out to be the most strict criterion usually in practice. So in practice, he says you design using the deflection criterion. You say, okay, how big a beam do I need so that it won't deflect too much, won't sag too much under the load? And then after that, so that's a stiffness criterion. And then you check whether the strength criteria are satisfied, and if they're not, then you go back and make a correction. So what we're going to do when we start next time is we're going to do some geometry and some math, and we're going to try to figure out what it is that determines the shape that a beam deflects into when you put a load onto it. So it's going to be a little mathematical adventure we'll do in the next video. Okay, so we'll see you in class, and this is the adventure to look forward to in the next video.